Hello, everyone. This is Donna Lalonde from the American Statistical Association, and I'm delighted to be able to welcome you to this second webinar featuring articles from the Chance special issue, Nurturing Statistical Thinking Before College. We at the ASA are really very pleased to be able to bring you this content. Also feel very fortunate to be able to introduce our speaker, a presenter. Zalman Yusiskin is Professor Emeritus of Education at the University of Chicago and absolutely a legend to those of us who have been in mathematics education. So it's a real thrill to be able to listen to his presentation tonight on applying statistics across the curriculum. Dr. Yusiskin has spoken at conferences and colloquia all over the United States and in 25 foreign countries. He has received numerous awards, so we indeed feel fortunate that he's going to share his expertise with us tonight. So with that introduction, I will turn it over to Dr. Yusiskin to share his wonderful presentation.
Thank you so much. I wish to thank the ASA and Chance for this opportunity to share some thoughts with you about the relationship between statistics and other school subjects in kindergarten through grade 12. My remarks stem from three premises. The first is what I believe to be a truism to most of us. Statistics are found and applied today in almost every domain of human activity. My second premise is probably not believed by everyone listening. The fundamental ideas of statistics, including variability, randomness, the laws of probability, and so on, are accessible to virtually all students. Even if you think that not all students can learn the basic ideas of statistics, I believe school policy should operate as if they can and give them the opportunity. The third premise comes from the GAZE document of the ASA of 2007. And that is that every high school graduate should be able to use sound statistical reasoning in order to cope intelligently with the requirements of citizenship, employment, and family, and to be prepared for a healthy, happy, and productive life. And I think the key word in here is every high school graduate. In most places in the world, despite wonderful strides over the past generation, it's not currently the case that all high school graduates are familiar with the tenets of sound statistical reasoning, let alone able to use them. In many places, only a small minority of students are exposed to these ideas. Statistics is not a traditional subject at the K-12 level. The subjects that are in the curriculum compete for time. And so the basic question that I attempt to treat today is how and where should we teach statistics when there are so many other subjects competing for this time? A half-century ago, and still in many school situations, the answer to this question was simple. Statistics was viewed as a branch of mathematics like algebra or geometry, so teach statistics within mathematics. And basically, to answer this question, I'm going to give a historical perspective, for the most part, a U.S. perspective. The view of teaching statistics inside mathematics is reflected currently in the TIMSS International Studies and its ancestors, and in the U.S. Common Core Standards Initiative, where the mathematics content is split into 3 or 5 categories, and statistics and probability or data is one of those categories. In this view, we teach statistics within the time frame that is allocated to mathematics and test statistics along with mathematics. There are at least 3 reasons why we'd want to teach statistics within mathematics. First of all, statistical formulas involve mathematics, and so why would anyone not think of statistics as a part of mathematics? Secondly, statistics is in many, if not most schools, a relatively new area of study in the curriculum. On the other hand, mathematics is a fixture. So the school day is limited in time. There's competition for time that's available. If we fit statistics within mathematics, although we have to compete with other areas of mathematics, we don't have to carve out a separate time in the day for statistics. And third, mathematics is tested everywhere, so it's taught everywhere. Topics that aren't tested are easy to omit, and it's difficult to build on previous year's work if you can't be certain that this work was actually taught. So if we place statistics within mathematics, we can be more confident that statistics will be tested and taught. The view of statistics as a branch of mathematics is the view of statistics that I was educated to have. When I went to school in the 1950s, yes, that long ago, very little statistics was taught in mathematics courses in grades K through 12 in the U.S. By the end of grade 8, a student could expect to have seen bar graphs, circle graphs, and line graphs, but the notion of collecting your own data for such graphs was absent. The only statistical measures taught were the mean and the median. In grades 9 to 12, non-college intending students would likely see these topics reviewed, but college-intending students would see no statistics in their math courses and no statistics outside those courses either. Through my undergraduate career as a math major and a statistics minor, all of the statistics I learned was inside mathematics courses. In graduate school, though I used the statistics commonly found in the educational field, such as hypothesis testing with t-tests, analysis of variance, and the like, these were taught as statistics for specialists, and they were not viewed as the kind of stuff you would learn before college. I've believed strongly that all students need to encounter a significant amount of statistics in their schooling, starting in the earliest grades. And the most likely way that students would encounter this content would be to embed the content within the mathematics curriculum. Reflecting this view, in my curriculum work for over 40 years, I've tried to match traditional topics in the math curriculum with related ideas from statistics, and going in the opposite direction, looking at basic ideas from statistics for the mathematics involved in them. This table shows a number of traditional mathematics and statistics topics that go together. There's nothing particularly inventive about finding these connections, but teaching them together often requires careful thought and raises non-trivial questions. For instance, let's take an easy connection. Euclidean geometry tells us that there's exactly one line through 2 points. And if those points are identified on a coordinate plane, it is a standard algebra topic to find an equation for that line. It is appropriate mathematical thinking to ask, what about finding an equation of a line through 3 points? Typically, those 3 points will not lie on the same line. So what about finding an equation of a line that's closest to the 3 points? It is a beautiful and natural way to get into the line of best fit through n points, and that generalization is something we all know. However, the algorithm for finding the line of best fit is not at all like the algorithm for finding the equation of the line through 2 points. At the secondary school level, the line of best fit cannot be done with the same sort of attention to understanding the algorithm as the line through 2 points. Furthermore, the geometry is not the same. Why do we examine the square of the vertical distance from a point to a line rather than just the perpendicular distance from a point to a line? Why is the line of best fit for n points xy usually not the same as the line of best fit for n points yx? That is, with the points with the coordinates switched. The geometry has different criteria for distance than the statistics, where a level of prediction is involved. Sometimes there are surface connections between the mathematics and the statistics that are not easy to explain, such as why e, the base of natural logarithms, is the base of the exponential expression in the formula for a normal distribution. On the other hand, there are times when the statistics can precede the corresponding traditional math topic. The idea of mean absolute deviation can precede the introduction of absolute value and distance between 2 points on a number line. At other times, more than motivation is involved. Subscripts to identify student scores on a classroom test, such as S1, S2, and so on, are easier for students to grasp than the traditional X1, X sub 2, Y sub 1, Y sub 2 that are, at least in the U.S., traditionally introduced when the formula for the slope of a line is to be studied. Why is it easier? I think that it's easier because when there are scores, when there are 25 scores, the subscripts make it obvious that these are identifying the scores. These are names for the scores. But when there are only the 2 subscripts, X1 and X2, the naive student confuses the subscript with the exponent and looks to do some sort of calculation with the 1 and the 2. At times, the traditional application of an idea and the use of the idea in statistics are quite complementary, helping each other out. Scaling data and scaling graphs of functions and relations involve the same mathematics. The formula for standard deviation helps students to realize that square roots are found in other places than right triangles. The examples I just given are from the later half of the K-12 experience, that is, from middle school and high school, but there are numerous connections between statistics and the mathematics of earlier grades, some of which are in this second table. All in all, the many places in which the mathematical ideas in statistics can be associated with topics in the traditional math curriculum are quite fruitful for the teaching not just of statistics, but also for the teaching of traditional mathematics. And it's been a major impetus for introducing some statistics into the curriculum. But how well does statistics fare in an environment where it competes with other mathematical areas, such as arithmetic, algebra, and geometry? Consider the most recently published TIMSS from 2011. At grade 4, there are 3 item content categories: number, geometric shapes and measures, and data display. Data display items constitute 15% of the total score points available. At grade 8, there are 4 content categories: number, algebra, geometry, and data and chance. And data and chance items constitute 19% of the total score points available. For another comparison, consider the Common Core state standards. At grades 9 through 12, the number of standards in statistics and probability is about 20% of all standards. You can see that in the right column here. And at grades 6 through 8, it's about 23%, 19% in statistics and 4% in probability. And at grades 1 through 5, it's about 5% is in data. There's no separate one for statistics at grades 1 through 5. And except for these grades 1 through 5, this is an extraordinary inroad into a math curriculum in the U.S. that in the past has tended to be very traditional and difficult to change. It's hard to imagine the math curriculum giving much more attention to statistics than this 20% or so, except at grades 1 through 5, where the Common Core has simply missed the boat on data. But even with the difficulties in the Common Core in grades 1 to 5 to be worked out, and even were all the GAZE recommendations to be accepted in schools, the approach to place statistics within mathematics has difficulties, primarily because statistics spills over quite a bit beyond mathematics. And so a second way to view statistics in the K-12 curriculum is as applied mathematics. Teaching statistics as applied mathematics recognizes that, like other areas that we identify as applied mathematics, areas such as operations research, computer science, or even physics, the issues and problems statistics treats originate from outside mathematics. So like these other areas, the issues and problems originate from outside mathematics. They're not taught simply because you think it's nice for students to learn about ideas such as center spread, variability, distribution, and the like. They're taught because we want to learn about these outside ideas. The process of mathematical modeling used in applied mathematics has often been depicted in a diagram similar to the one that's shown on this slide. In the mathematical modeling process, the basic idea is that one goes from the real world into the world of mathematics, works with the model in the mathematical world, and then goes back out into the real world to check the obtained results with reality. How does this differ from teaching statistics within mathematics? Well, in teaching statistics within mathematics, the motivation for the idea might come from a mathematical idea we wish to reinforce. For instance, we might introduce the idea of mean absolute deviation just after or just before we teach absolute value, and examine the idea for its theoretical properties without much concern for the application. But if we are to teach mean absolute deviation as applied mathematics, then the problem needs to arise from outside mathematics. So we look for one or more real situations in which the concept of spread is meaningful. One of my favorite modeling problems for grades 6 through 9 is to examine the question of when a person should leave from home to the nearest airport in order to be on time for a flight. Let us suppose that the departure time for a plane flight is 10 o'clock A person is driving to the airport and will leave a car there. We'll call the departure time D, so D is 10. We can identify some variables. Let L be the time to leave, get to the gate G minutes before departure. Let T be the time to travel from home to airport, and let P be the length of time to park your car. Let S be the let B be the time for getting a boarding pass, and let S be the time to get through security. It seems like this problem is a pure subtraction problem working back from the time of departure, 10. So it's 10 minus the quantity G plus T plus P plus B plus S. But what happens is that statistics comes into it immediately. Because T, P, B, and S all vary. The travel time from home depends on the route and the traffic. If someone else drives you to the airport, then P is 0. If you print your boarding pass from home and don't check bags, B is 0. The security time may range from a few minutes to 30 minutes or more. The problem begs for some actual data. How does T vary? With GPS tracking today, it's possible to collect data about travel times on various routes over a period of days without having to do the travel. What about the security time, S? It is possible and would be interesting to collect data on the length of time it takes passengers to get through security. I'm sure somebody is collecting this data someplace. For both T and S, we would be particularly interested in measuring the spread of the distribution of times. Measures of spread become appropriate because of the need to factor in a person's tolerance for risk. As nice as so many examples like this one can be in a math classroom, there are problems with approaching statistics either as a subfield of mathematics or applied mathematics. The mathematics curriculum is crowded. It's not a curriculum with loads of room begging for topics to fill it. Even statistics units within math courses tend to be devoured by other mathematics. Many mathematics teachers are uncomfortable with statistics. They're uncomfortable with the lack of certainty arising from statistical situations. It's difficult to incorporate into traditional algebra, geometry, or analysis questions of sample selection, more than the simplest kinds of exploratory data analysis and the interplay between the degree of confidence in a statistic and the length of the confidence interval, and many other rather basic ideas of statistics, even mathematical ideas that take some time to develop. Statistics has its own body of knowledge separate from mathematics. As a result, within a math course, you can develop a taste for statistics, discuss basic notation in some language, and show how one needs mathematical knowledge to treat statistics. But for intense study, statistics needs its own courses, even at the pre-college level. And that's the third sort of possibility here, that is to teach statistics as an independent subject. Of course, at the college level, the idea of treating statistics separate from mathematics or applied mathematics has been with us for some time. It's gained some traction after the Second World War. I don't know the first university in the world to form a statistics department, but such departments were initiated at Columbia University in 1946, at the University of Chicago in 1949, and at Harvard in 1957. Perhaps this has been a more U.S. phenomenon than in other countries because it took until 1988, 30 years after Harvard, for Oxford to have a department of statistics. At the same time, many other colleges and universities in the U.S. broadened the name of the mathematics department to mathematics and statistics, mathematical sciences, or even some with the name mathematics, computer science, and statistics. Shortly after the Department of Statistics at the University of Chicago was created, perhaps to emphasize the difference between statistics and mathematics, two of its faculty, Alan Wallace and Harry Roberts, described statistics in a way that does not mention mathematics. They said, statistics is a body of methods for making wise decisions in the face of uncertainty. Their view of statistics was quite a departure for its time, which was 1956. They continued, this modern conception of the subject is a far cry from that usually held by laymen. Indeed, even the pioneers in statistical research have adopted it only within the past decade or so. The view of statistics as its own body of knowledge, related to but separate from mathematics, dominates many introductory courses at the college level today. It's reflected in the simple description of statistics found in one popular college textbook and many other places. Statistics is the science of data. The Gaze report emphasizes this break from mathematics. A major objective of statistics education is to help students develop statistical thinking. Statistical thinking, in large part, must deal with this omnipresence of variability. Statistical problem solving and decision making depend on understanding, explaining, and quantifying the variability in the data. It's this focus on variability in data that sets statistics apart from mathematics. This position of statistics relative to mathematics is somewhat like that of physics relative to mathematics. It's impossible to do much physics without knowing mathematics, and it could be said that physics is the application of mathematics to the study of matter and energy and their interactions with various forces. Yet there is so much to physics that is not mathematics that almost everywhere physics is studied as a subject in its own right, not as part of a mathematics course. This belief in statistics as its own field of study in high school, separate from mathematics, began to take hold in the United States within the last generation. Perhaps someone listening to this webinar has knowledge about the percent of high school students in the U.S. who graduate with credit for at least one semester of statistics. The best data that I could find from the National Center for Education Statistics dates from the high school graduation class of 2009 and groups probability and statistics and trigonometry together under advanced mathematics, indicating that 30% of graduates have earned at least one credit in this area. This compares with 35% who have credit in pre-calculus mathematics and 17% who have at least one credit for calculus. So I guess I have 16 on the slide, 17. Maybe it's somewhere in between. The Advanced Placement Program, by which students take the equivalent of selected college courses in high school, are given national tests on each course, began in 1955, and calculus was there from the beginning. The Advanced Placement Program in Statistics began in 1997, and since the year 2000, the number of students taking the exam has increased by about 10% a year. By last spring, almost 200,000 students, or about 5% of all high school graduates in the U.S., were taking the Advanced Placement Statistics exam, and perhaps an equal number were taking the course without taking the exam. When the statistics exam was first offered, I'm certain there were those who felt that enrollments in the calculus exams would fall. But as the data on this slide indicates, there are now 303,000 students in 2015 who took the AB calculus and over 100,000 who took BC calculus. These increases in advanced placement statistics haven't come at the expense of taking AP calculus. Since 2005, more students in the U.S. are enrolled in calculus courses in high school than in college. Almost all of these students take these statistics and calculus courses in grades 11 or 12. But these courses are college-level courses. Full courses devoted to statistics at the high school level seem to be less common. Furthermore, by including statistics as part of the Common Core standards in the U.S., the movement for a separate course may have been slowed down. Nevertheless, the history of school mathematics around the world is that the content we teach now to students in primary and secondary schools used to be taught to much older students. New content often appears first at the college or advanced secondary level and then filters down over the years, decades, and centuries. So it has been with arithmetic, algebra, and geometry, and so it is with statistics. It is quite likely that within a couple of generations, most of the content of the course in introductory statistics at the college level will filter down to become standard school content. At the same time that the movement towards statistics courses in the secondary school was beginning, there was a concerted movement to reach students who in the past dropped out of their study of mathematics quite early in schooling, say after grade 9. In the U.S., the slogan was embodied in the title of the report, Everybody Counts, a 1989 report from the National Research Council. Worldwide, there were the mantras, mathematics for all, algebra for all, In this arena, there arrived Statistics for All. In the same year as Everybody Counts, that's 25 years ago, the view that statistics is important in the early grades is represented in a UNESCO publication based on presentations at ICOTS 2, that is the International Conference on the Teaching of Statistics, second one. A strong theme of this publication is Statistics for All, with articles on the exploration of data, on quantitative literacy, and many other interesting contributions. It's significant that these themes were laid out before the first public access to the Internet in 1990, before public email, before Facebook and other social networks, before mobile phones and apps, that is, before the accessibility of data to everyone, and before big data. In the work of these and many other people, we see the move to introduce the collection and discussion of data early in primary school, and the desire for grades 6 to 8 to be a particularly useful time for the introduction of more formal statistical concepts. As the years go on, we see more and more confirmation of the belief that because data is present everywhere, the study of statistics has implications for the study of virtually every other discipline. This is nothing new for statistics at higher levels. But as the years have gone on, consideration has been given to younger and younger students to teach statistics across the curriculum. For instance, the Royal Statistical Society in 2005 spoke about teaching statistics across the curriculum. Even at the earliest grades, a strong case can be made for treating some basic statistical concepts inside disciplines other than mathematics. First, it's important for all students to learn reasons for statistics early, and these reasons are embedded in the understanding of other subject areas. Second, statistics has different associations with the major subject areas of early education. Third, particularly in the early grades, in most places many of these subjects are taught by the same teacher, making cross-subject teaching easier to implement. Here we're speaking of students of ages 6 to 12, young students. The school curriculum for students of age 6 to 12 consists mainly of language arts, that is reading, writing, and speaking, mathematics, social studies, which includes history, government, geography, and economics, science, which includes physical science, biological science, and earth science, and health and physical education. When we think of the school curriculum at these early grade levels, we think of what all people need to know for survival, as well as grounding for more advanced work. Other subjects at the early grades may include the study of foreign languages, fine arts, applied arts such as woodworking and cooking, and in some places moral and religious education. I cannot make the case for incorporating statistics within all of these areas, but I would like to mention a few ways to support the general theme of statistics across the main subject areas. First, let's begin with language arts. Language arts covers reading, writing, and speaking the language or languages of discourse in one's country. Throughout the world, language arts understandably dominates the school curriculum in the first grades. In the U.S., the amount of time devoted to language arts is 2 or 3 times the time devoted to mathematics, the subject receiving the second most attention. It's in language arts that students are expected to attain basic literacy. We want citizens to be able to read and listen with understanding to a fictional story or non-fictional news account, to be able to digest critically the information they hear or see. It's not coincidence that in the Gaze report, the first reference to statistical literacy concerns what is reported in a newspaper and in other media. The amount of information in a single issue of a daily newspaper can be staggering. How many numbers are there on a typical page of a newspaper? This is an interesting question for statistical analysis. What do we mean by newspaper? So what's our population? How should we select a sample? I decided not to do a rigorous statistical study, but just examine one day's newspaper and count all the numbers myself. I picked what I considered to be a typical day of a large city newspaper that I received daily, Thursday, February 6th of last year, of the Chicago Tribune. I then tried to determine the number of numbers on every one of the 64 pages of the main 6 sections of the newspaper: news, business, sports, arts and entertainment, dining, and automart. I did not include 70 pages of advertising inserts. Now that I had selected the newspaper and the pages, the next question was, what's a number? Is a word name like, quote, first, F-I-R-S-T, end quote, or 300 written out, or millions, is that a number? Is a telephone number 10 numbers, or is it 4 numbers, 1 number, or not a number at all? Is the score of a basketball game to be counted as 2 numbers or 1, and so on? An interesting question. So the slide shows some of the decisions I made. I decided first was a number, so it was 300 and millions. And a telephone number, I decided was 1 number. You have a telephone number. A score, on the other hand, is 2 numbers, an ordered pair. A word name like several is an estimate, and I counted it as 1 number. July 3rd, 2014, whatever a date is, I counted as 1 number. A product code name, I counted as 1 number. The word none, however, I thought is not a number. And the word one could either be a number or it could be just an abstract person. One thinks that it might be either. The word double is a multiplier of 2, and I counted that as a number, the word name for 2. And half is a fraction, it's 1 number. The number of numbers on a page of a newspaper I had selected, of this newspaper, ranged from 13 on the first page of the dining section, which was a page dominated by a large picture of a dinner plate with food, to 2,278 on a page containing sports results. The total number of numbers was 13,518, so the mean number of numbers on a page was just over 211, with a standard deviation of about 426, and the median was 72.5. So there are loads of numbers in the newspaper. But is there statistics? Numerical literacy does not guarantee statistical literacy. Fortunately for us, the newspaper is rich with examples of discussion of decisions made based on analyses of data. I'll mention a few examples and indicate some questions the examples might raise that relate to the study of statistics. The examples are mostly understandable at early grades. The questions can range from those grades to the college level. On the 4th page of the first section, a report on the Chicago area mass transit system includes 2 maps showing census block areas underserved by mass transit. Why are the data organized in this way? Why by census block area? On the 8th page, a summary of changes in police staffing reports a slew of data. The numbers of officers and supervisors assigned to work in 22 patrol districts over the past 5 years. Why is the timeline so important? There's a survey of Hispanic Americans regarding their views on upward mobility in the economy. Unusual is that the actual survey questions are shown in the newspaper along with their responses. The editorial is about the question of government-sponsored health insurance and the incentive to work, responding to a report from the Congressional Budget Office, the CBO, in Washington. The subhead of the editorial is, what's behind the CBO numbers? This leads to the natural question, what answers are given in the editorial? What is behind it? Half of a business page is devoted to a summary of the stock market action from the preceding day, with a line graph, 3 bar graphs, and lots of data about most active stocks, those most held, those with the largest capitalization, and more. I don't need to mention anything more about this, but how are these data collected? Why are these particular attributes of the data chosen to be presented? The lead article of the business section 2 is about the decision by CVS, a major pharmacy chain, to stop selling tobacco products. There are graphs of the number of cigarettes sold and the total retail value of cigarettes for each year since 1998, and a circle graph of the distribution of sales of cigarettes in gas stations, drugstores, supermarkets, convenience stores, specialty tobacco stores, and elsewhere in 2012. What trends do these show? And how did these trends fit into the CVS decision? Of course, the sports pages contain a lot of data. One unusual chart is a listing of the top 10 football signing classes. That is a ranking of the universities that are thought to have recruited the best high school graduates that year, according to the website 247sports.com composite ranking. Alabama is thought to have had the best signing class. LSU second. How are these ranking systems created? What's the significance of Arrow's paradox for combining ratings into a composite ranking? In addition to the results of games, the sports section contains a huge amount of statistics about teams and players. Why are particular statistics displayed? Which statistics are most important? The arts and entertainment section has a lead article that's about the artwork of a deceased painter whose family wishes to sell his paintings. How do statistics play into the development of asking and selling prices for paintings? The weather page is filled with forecast temperatures, amounts of precipitation, some bar graphs about record snowfalls. It's a Chicago newspaper, of course. Since weather varies from spot to spot, even within a small geographic area, the numbers can provoke a good discussion about their accuracy and variability. Thus, in this single day's newspaper, there is much data available for examination appropriate not only for the early grades of schooling, but also later. This demonstrates that both numeracy and statistical literacy are necessary for general literacy. And it demands that we promote the teaching of some statistical ideas inside the teaching of language arts in the areas of critical reading and critical listening. When reading data in a newspaper article or hearing data spouted on television news, we want to attune students from the earliest grades to ask, where did this number or these numbers originate? Is the number an exact value or an estimate? If an estimate, how might the estimate have been determined? What does the number tell us about the situation? How could the value of the number or the reliability of the estimate be verified? And so on. The subtleties of language found in surveys provide wonderful opportunities for the teacher of the native language. In that increased sophistication, there needs to be a discussion of how the wording of a survey item can significantly influence a response. When I tell my colleagues who teach literature that people in the mathematical sciences are at least as attuned to the meanings of words and the subtleties of interpretation as our poets and novelists, my friends in literature are very surprised. This is a role for the teacher of language, grammar, and writing in the upper grades of schooling. Why should we who are passionate about statistics education want to encourage putting this content into language arts? It's to show that the collection of data is a normal activity done by people in all walks of life, in government, in business, in entertainment, in sports, in everyday activities. It's to encourage students to collect data in situations that are pertinent to their lives. It is to counter the notion that statistics are just for those who are good with numbers. It is also to counter the notion that statistics are routinely collected and used for sinister purposes, the all-too popular notion that people routinely use statistics to lie, the notion that's perpetuated so often that there is a Wikipedia article titled Lies, Damn Lies, and Statistics. When I Googled that phrase, I got 592,000 hits. Now let's move on to the social sciences. As ubiquitous as the uses of statistics are in everyday events, so are statistics everywhere in history, geography, economics, and politics. That is, in the social sciences. Even when I was a student over a half-century ago, it was in social studies, not mathematics, that we learned to read bar graphs, circle graphs, and line graphs along with the reading of maps. What are some broad statistical principles that can be best brought out in social studies? One is the variability within groups and the danger of characterizing an entire group by its central tendency or by a distorted sample of its membership. Long-term and short-term trends over time are often eye-openers for young children, from the human population on our planet to the number of cell phones in use. A helpful source of data in some countries can come from the Census at School International Project of the Royal Statistical Society Center for Statistical Education. Whereas the wording and grammar of opinion surveys is appropriate for language arts study, the intent of an opinion survey is more in the area of social studies. Why are there polls before elections? How do pollsters determine who they poll? How are TV ratings gathered? And so on. The teaching of health and physical education calls for a discussion of statistics about longevity, about what might cause and what might cure disease, and about what data supports a healthy lifestyle. It also begs for a discussion of anecdotal evidence of the occurrence of events with very low probability for individuals in a large population. Perhaps some of you are familiar with the book by David Hand published last year, The Improbability Principle, Why Coincidences, Miracles, and Rare Events Happen Every Day. Both in health and in the social studies, one can discuss the dangers of extrapolating results from one population to other populations. I've left science as the last of the big subjects taught in the early grades because the collection of data in science courses is a long-standing practice. From simulations of Mendel's experiments with peas to replicating Galileo's experiments with inclined planes in physics, I think that it is the case in many schools that so little statistics is taught within mathematics that more statistics is taught in science than in math. In the U.S., unlike the situation with the Common Core standards, statistics is found in all grades, kindergarten through grade 5, in the Next Generation Science standards that were released in 2013. A section of the kindergarten standards reads that in the kindergarten performance expectations, students are expected to demonstrate grade appropriate proficiency in asking questions, developing and using models, planning and carrying out investigations, analyzing and interpreting data, designing solutions, engaging in argument from evidence, and obtaining, evaluating, and communicating information. Students are expected to use these practices to demonstrate understanding of the core ideas. A similar pair of sentences appears in each of grades 1 through 5, and in each grade these expectations are detailed. Since the 1980s, there's been a movement both at the school level and at the college level called writing across the curriculum. The idea is to use writing as a learning tool in the various disciplines, as well as recognizing that in the disciplines there are characteristic and sometimes unique writing conventions. For instance, writing a mathematical argument is quite different from writing a biography. Statistics can be viewed as similar to writing in spanning the curriculum. Writing has its home in language arts, and we can say that statistics has a home in mathematics. And just as the style of writing varies dependent on the discipline in which it's being used, so does statistics vary. This is not a new idea. Over 20 years ago, a supplement to the mathematics standards of the National Council of Teachers of Mathematics was titled Data Analysis and Statistics Across the Curriculum. The intent of that supplement was to show that there were examples of data analysis and statistics in a large variety of subjects that were taught in school. I think a next step is needed to go beyond examples within the time allotted for the teaching of statistics into the time allotted for the teaching of language arts, social studies, science, and health, so as to teach students that it's not just for learning statistics that one looks at these examples, but that for learning these other subjects, statistics is necessary. In summary, statistics has at least 4 kinds of places in the school curriculum relative to the other subjects. Its traditional places as a part of mathematics, a more accurate place as applied mathematics, as the science of data studied for its own sake, and across the curriculum in understanding the main other subjects of the curriculum. We need to strive in all these ways so that all students, whether they wish to study psychology or physiology or education or law or nursing or any number of other fields, or be a farmer or laborer, or if we wish only for them to be informed citizens, whether or not they finish their formal schooling before college, that they will understand the breadth and importance of the careful understanding of data. Thank you for participating in this webinar, and now I think we're ready for some questions.
Absolutely, and I want to thank you for sharing these your wonderful talk with us. And the first question also wants to acknowledge how great the paper was in this special issue. The question goes back to your comments about 20% of the Common Core reflecting curriculum in statistics, and says that in New Zealand, for example, about 1/3 of the standards are stat standards, and wonders if you feel like the New Zealand experience is relevant to us.
Well, I'm not familiar with what that 1/3 entails. The problem that we have is there's really a lot of good mathematics other than statistics. I mean, I know in this audience we might not want to think that, but there really is a ton of great mathematics, and a lot of it. And the problem that I see is that if we rely on mathematics as the place to teach statistics were limited. And so I do not at all disagree with the idea that, raising from 20% to something else is appropriate. In fact, that's really part of this talk, that it should be raised, but not necessarily within mathematics. That you want to have some statistics in the other subjects as well.
Following up on that, it's a question about whether or not there's a need for another bubble, and that additional bubble would be computer science, and the questioner comments on the new advanced placement course in computer science principles, and the emphasis that we're seeing in some cities, in New York, for example. Wonders about your thoughts about where computer science fits. Do you see that fitting within science, or do you think that another bubble is necessary and the role statistics would play in that new bubble?
Oh, that's an interesting question. Well, from a lot of perspectives. Let me first tackle, at least give an opinion on the advanced placement aspect of that. I think it'd be very interesting as to whether that cuts into the statistics advanced placement numbers. There's only so many courses that students can take, and one wonders whether, given the choice between that, because that second computer science course, they're not doing away with the traditional computer science AP exam. This is a second exam, and one imagines that this exam is almost in the same vein as the thought that the statistics would be for those students who might not want to go into calculus. They would have a kind of mathy AP exam, and that would be the statistics AP. So it'd be very interesting to see what happens there. We don't know, of course. We haven't even had the first year of this second exam. Now the question of whether of computer science across the curriculum or how it interfaces with statistics is one that I really haven't thought about. And you can tell from this webinar that I hadn't thought about it, because I don't think I mentioned computer science once. That doesn't mean that it isn't important. But I think it has some of the same problems that statistics has had, the same history of starting out being embedded. Actually, it was either embedded in mathematics or sometimes in some places it was embedded in electrical engineering at the very beginning. But then fairly quickly it seems to have gotten into some math departments and then split off in some places and still is a part in others. It's only going to grow. I mean, it's like statistics. These are our two modern contributions to knowledge.
A number of people really appreciated the newspaper example and wondered if you have explored the potential link between language arts and data journalism efforts. Someone even mentioned our colleague Rob Gould's Mobilize program in LA, but the connection to data journalism.
Well, I don't know of too many programs that do this. I do know that Miami University in Ohio has had such a course where it's taught by someone who's a statistician and someone who is a journalist. And I remember hearing a report of that course, and it was a real eye-opener for both of the people teaching the course. Mm-hmm. It started out because of a statement made, I think, about 10 years ago of someone who was working for the New York Times who had stated that there wasn't a person on the editorial staff who was really proficient in statistics. Mm. This is the New York Times.
Right.
It's, so you would think that would have been the place where you would have had somebody. And so the need for journalists, is there a need for them to know statistics? We all know that.
Maybe this is where I put in a plug for stats.org, one of the initiatives of the ASA to actually reach out to journalists.
What we need is journalists to reach out to us.
Right. That's right. Absolutely. We have a question that says, I've taught statistics using computer science, primarily R. Is there a trend developing in this area, or am I an outlier?
Oh, well, I can answer the last question. You're of course an outlier. Every person is an outlier in some way or another. I don't know if that's a trend. R is certainly a trend. I don't know if the way you're using it is a trend.
I think that is the questions that we have. I'll give folks just a moment in case they want to share any additional questions. Maybe while I'm waiting, I'll ask one of my own. So it seems like a lot of times when to do a cross-curriculum endeavor, it's the getting started. So do you have any advice for teachers in how math teachers, statistics teachers, how to do that outreach to their colleagues?
Well, I think the first thing is, in fact, to just do it. Advise me that you're willing to do it, that you want to do it, that you're very interested in helping them to do their teaching better. Not that you have something, that you have the magic potion here. I think that's very important. If you're trying to embed something that you know into someone else's curriculum, it's really important that they view it as enhancing their curriculum, not as just serving you. I'm reminded, for instance, that just in the last, recently, I became aware of the wonderful hour-long talk, I think it's by a Swedish statistician, about the casualties in World War II. And I wish I could just give you the name and about it, but maybe one of the people listening can give that. And this is an eye-opener for anybody who is studying world history. It's an absolutely fantastic hour, and you learn more in this hour than you would reading so much about wars and peace and things like that. So I think if one can say, I've got something to a history teacher, let's say, you might be interested in, that kind of thing. Not that I think that I want you to teach statistics, but you might be interested in this. You know what I'm saying?
Sure.
Help them rather than trying to ask them to help you.
Right. Well, thank you very much for sharing your time with us. I see the slide that indicates that PowerPoint is available if folks send an email to that email address.
That's right.
And we will be posting the recording of the webinar. So thank you so much.
You're welcome. Thank you. Thank everyone who's listening.
Thank you.
Bye.
And I think that concludes our webinar for this evening.